Okay, so today we're going to talk about Grover's algorithm. It first appeared in something like 1995, and it in a paper that was titled "A Fast Quantum Mechanical Algorithm for Database Search." Which is a title that sells the usefulness of the algorithm short. In other words, this was probably the wrong title for the paper. What does Grover's algorithm do? So suppose you have an unsorted list, which is somehow in quantum memory. And one of the items is marked. Find marked item. So actually, if you have a list of things, you really don't want to use this algorithm, because first, what you can do is you can just take this list, you can sort it, and then you can access any item you want in time log n. And, or rather, you can check whether an item is on the list in time log n. And if you have a list of n things, then putting them in quantum memory is going to take n time, unless you can somehow do it quantum parallelly, which is, I don't know, only works for certain kinds of lists. And it takes of square root of n list of n things time, which is much slower than you could do with a real classical database. So where is Grover's algorithm work? Well, it works for finding, I guess, implicit lists. So suppose you want to find x, y, z, w with x to the fourth plus y to the fourth plus z to the fourth equals w to the fourth. And you know there's a solution with x, y, z, w less than 1 million. Classical time. Well, actually, this was done by a mathematician using, I don't know, a clever idea. So there are better ways to do it. But classical time by brute force. On the other hand, this was an open question for, I think, 200 years before Noam Elkies found a solution in 1986 or so. So the classical time by brute force, well, I mean, if you have a random x and a random y and a random z, you can take the fourth power and add them up and take the fourth root of that and check whether it's an integer. So you only really have to search over 10 to the 6th times 10 to the 6th times 10 to the 6th things, 10 to the 18th. But Grover's algorithm can search this list in time, well, roughly 10 to the 9th. Small constant times 10 to the 9th. So that's our, 10 to the 18th trials of this thing, and Grover would take 10 to the 9th trials of this thing. Yeah?
But that's assuming that that's assuming the worst case scenario, though, right?
Yes.
That you find it only on the very last pair you try.
Right. So on average, it would be maybe 1/2, 10 to the 18th. And in case you're interested, we're not going to test you on this. 1 to the 4th equals 4,14560 to the 4th plus 2,17519 to the 4th plus 95800 to the 4th. Assuming I didn't copy it wrong. So right now, we're going to assume there's only one solution. Right now, assume one solution. In n things. And later, we will tell you how to do it. It's actually faster with m solutions. And we assume, let's see, what is our name? Okay, so assume beta is, yeah, okay, good. So assume beta is our solution. And assume we have an oracle of a black box function. Box unitary. And let's call that O. And O x equals x, x not equal to beta, and O of beta equals minus beta. So this is a phase oracle. But we showed you how to get a phase oracle from a bit oracle back when we were discussing Deutsch-Jose. And the way you would use a phase oracle for this is basic, for this problem, is you would take x, y, z. You would classically take the 4th powers and then take the 4th root and decide whether that was an integer. And if there's an integer, you apply the minus sign, and then you undo that all to get rid of the garbage. So the only thing that's left that you've actually done is you've applied a minus sign when beta is a solution. So there's lots and lots of time spent looking for good solutions. So what we're assuming is that if we have a solution, we can recognize it. And that's all we're assuming. And that's very often the case. So this is, there's lots and lots of computer cycles spent on combinatorial optimization where you're looking for, some structure which gives you a good solution to an optimization problem. And you could use Grover's algorithm for that. Of course, it does not speed up the classical time exponentially. Classically, it's order n, and the quantum mechanical thing, it's order of square root of n. On the other hand, it's a guaranteed provable speed up that because assuming you can't take apart this oracle that tells you whether something is a solution or not, the best thing you can do just by exhaustive search is order of n time.